If somebody is traveling past you and tossing a ball up and down in the air, and if they're tossing the ball straight up and down as they perceive it, then the ball will follow a series of parabolic paths as you see it. We know that the ball goes up more and more slowly and then falls more and more quickly. If the person tossing the ball is moving at a constant velocity in this direction, then the parabolic shape is going to follow, and you can think about the details of projectile motion. The projectile motion is not real important here, just to give you a vivid picture. If we now have somebody moving past you, but there's a ball, let's say, bouncing from floor to ceiling very fast, so that it doesn't really lose any energy as it goes from floor to ceiling, and we somehow maintain a constant speed to this ball, we'll get a sawtooth path, sort of like the parabolic path, but the constant speed gives us these jagged peaks. Make sure that the motion is linear over every phase. Now, the velocity of the ball, or the speed of the ball, is going to be the resultant of the x velocity of the whatever vehicle the person might be riding as they go past, and the y velocity, the actual velocity of the ball. And the vector sum of these two velocities, of course, has magnitude that we obtain by the Pythagorean theorem. Now we use this as a prelude to think about what happens if we have a light beam being bounced from floor to ceiling. Okay, so we have a light beam bouncing up and down, and if somebody's moving past us fast enough, and they have to be going very fast, I guess we better have rocket ships and be out in space in order to do this, because light, of course, travels very fast. If somebody's bouncing a light beam from one mirror, from mirror on the floor to mirror on the ceiling and back and forth, and just letting the beam bounce very quickly back and forth between the mirrors, and if there's a detector at, let's say, the mirror on the ceiling, and let's say this detector, every time it detects the light hitting, emits some kind of a signal, a beep or an electronic signal, whatever. The path of the light, if the person is moving fast enough, will appear to be a sawtooth. We will observe a sawtooth. And I'm going to point out that the distance moved by the wave that we observe is greater than the distance moved by the wave as observed by the person in the rocket ship that's going past us, let's say. Okay? Now, the velocity of the light, we're going to say, is c. That's 3 times 10 to the 8th meters per second. Vx will be the velocity of the spaceship that's going past us. Okay? As seen by the observer. Now, in the ship that's going past us, the detector is going to beep every time light travels a distance equal to 2d. So that there's going to be a delta t between beeps that's related to the velocity here by the fact that the velocity of the light is 2d over delta t. The light travels distance 2d between detections at velocity v, and here's our delta t. In this case, if we let s stand for this distance, then the round-trip distance from detection to detection is 2s. And there's going to be a different delta t prime, provided that the velocity of the light is the same here as it is down here. Now, it's going to turn out that we assume that the velocity of light is the same. That's different than for a bouncing ball. The ball here has a velocity that's actually greater as measured along the sawtooth than as measured by the person who's bouncing it up and down, because the ball goes further in the same amount of time. We would think that might be the same for light, but there's a hitch, because Maxwell's equations, which as far as we know are completely consistent with everything we know about the universe and about physics, predict that the speed of light will be the same no matter who observes it, no matter from where it is observed. If we make the assumption that the laws of physics don't change from point to point, then Maxwell's equations do not allow us to distinguish the speed of light as observed in the ship where the light is bouncing up and down, and from our point of view where the light is following this longer sawtooth path. The velocity v is the same in both cases, which means that the delta t that we observe between detections is going to be different than the delta t observed between detections in the ship. So we're going to call the delta t that we observe delta t prime. The delta t in the ship we'll just call delta t. Again, we draw the conclusion that since this distance is greater than this distance, and since the velocity has to be the same, that delta t prime has to be bigger than delta t.